Okay, so in this video we're going to talk about the particle in a 2D box. So here this is 2D box. Like in the same 1D box system, we are going to put our potential energy infinite out of the box and potential energy 0 inside the box. So if you remember how we can represent the energy of a particle, it's by showing the equation, right? Here we have the Hamiltonian operator and we have the wave function energy, which is the eigenvalue of our wave function, right? So we have introduced this Hamiltonian operator, which is represented by minus h bar squared over 2m d squared over dx squared. This is for 1D box, right? This is for one dimensional box. When it comes to the 2D box, there are two axes, there are two dimensions, right? There are two dimensions, so we need to little bit change our Hamiltonian operator. Everything's same h bar, same 2m. This d by dx term we need to change it by like this: dabba squared over dabba x squared plus dabba squared over dabba y squared, because there are now two components, there are two dimensions, right? That's we have to introduce two terms over here. And now because of this has two dimension, we cannot use d, instead of d we use dabba, right? It's just the same thing, right? This and this both are the same thing, just the representation is different. Just don't mind that. So let's move. So the same thing, let's do the same thing over here, right? I'm going to apply this into our wave function, right, which is Hamiltonian operator times our wave function equals energy times wave function. Now here our wave function consists in two variables, right, which are x and y. So I will represent it by like this: x dot y. This is the x component of our wave function and this is the y component of our wave function, right? I will do the calculation in the later part, but just for now let's move forward with this, right? This contains the x part and this contains the y part of our wave function, right? So here I have introduced our Hamiltonian operator, h bar squared over 2m dabba squared over dabba x squared x y plus dabba squared over dabba y squared x y, right? Here I have introduced the wave function times e dot x y. Okay, now when we are doing a derivation respective to x, right, this y is considered as a constant because we are considering the x term over here, and same like the here we are derivate this function respective to y, so x is a constant. So when we are doing a derivation we can take out the constants. So here what I'm doing the same thing, we are doing the derivation respective to x, which means y is a constant, so I can take y out, dabba squared over dabba x squared, x inside, plus here the same thing, x is a constant, I am taking x out, dabba squared or dabba y squared component y, here e x y. Okay, now I'm going to introduce a small thing. I'm going to divide the whole expression by xy term, right? Here h bar squared over 2m, here I have 1 over x times dabba squared x dabba x squared. Here I have divided it by xy term, right? So here y to y I have cancelled out and x is left alone. So here we have 1 over y dabba squared over dabba y squared, here y term. equals, here we have to divide by xy term, so which means the both are going to cancel, right? I hope up to this point you are okay. Okay, now here look at this, right? This part over here, it is a completely x component, it's depend on x component, and this one here, it wholly dependent on the y component, right? You can see, uh, if I take this one over here, it will give the energy on x direction, and here this one with this is all multiplying this, right? This going to multiply by this, and this going to multiply by this, so this whole expression will give the energy on y direction. So I can split over here total energy into two parts. It is energy of x terms plus energy of y terms, right? So now I'm going to take this energy x and take energy y separately. Let's take it separately, right? Here we have energy x equal to y over x h bar squared minus 2m double squared over double x squared. Here we have x. Same likely I can take the y term out by minus 1 over y h bar squared over 2m double squared x, sorry, not x, y over double y squared. Okay, now if I take this x function, right? If I take this x function, which means the wave function in x components, right? Wave function in x component, we have talked about it, right? In 1D boxes we have talked about the wave function of a single dimensional problem. So how we represent it by here 2 over L1, which is here sine n1 phi x over L1, right? Here I have represent the wave function based on the x dimension, and same likely I'm going to represent my wave function based on y direction 2 over L2 sine, here I'm going to take n2 phi x over L2. Now I'm going to do the simplification based on this one, right? Let's first take the x component, right? Let's first take the x component. Okay, so here I'm going to do the derivation, right? So here this is our expression 1 over x times minus h bar squared over 2m times double squared over double x squared x. Now I'm going to replace this x by my original component, which is this wave function 1 over 2 L1 square root sine n phi x over L1 a1 times minus h bar squared over 2m times double squared over double x squared 2 times L1 sine n1 phi x over L1. Okay, now I'm going to do the derivation. You can see this is a constant, so I can directly take it out and it will cancel out with this one, right? So I'm going to cancel it out and I will write the equation sine n1 phi x over L1 times minus h bar squared over 2m. Now here the derivation, right? Now I have the sine n1 phi x over L1. So here we have two derivations, right? Let's do one derivation. With derivation sine convert to cos, and this inside part other than the x, we have to derivate the again, right? Here I'm going to derivate this Here I'm going to derivate this 1 times. So here we have taken out the n1 phi l1 and the sine derivation, which converts into cos n1 phi x over l1. Now we have to do the derivation again, right? Now this is a constant, right? This is a constant, so I can directly take it out. So 1 over sine n1 phi x over l1 times minus h bar squared over 2m times, I'm going to take this out, n1 phi over l1. Now the derivation, cos turns into minus sine, right? Cos turns into minus sine n1 phi x over l1, and I have to derivate this inside part again, times n1 phi over l1. Now here you can see this sine term and this sine term cancel out, right? This sine term and sine term cancel out. This minus term and this minus term becomes plus positive. So h bar squared over 2m times n1 phi l1, the same term, so I'm going to n1 squared phi squared over l1 squared. Now this is the only thing I am left with, right? So now I'm going to do some substitution. You know h bar, which is h over 2 phi, so I'm going to substitute h bar by h over 2 phi, h squared over 2m 4 phi squared dot n1 squared phi squared over l1 squared. This phi squared going to cancel out with this one, so I'm going to left with n1 squared h squared over 2m l1 squared. So to 8, this 4 will go out with 4 will multiply by 2. Right here I got the first energy component with respect to x. So you can do the same thing for the y term also, right? The same derivation is happening over here too. So I'm not going to do the derivation again. I'm just wrote the I will just write the expression right here. The y term is equals to n2 squared h squared over 8m l2 squared, right? So now you know the total energy is given by these two energy components combined. So I am going to combine those two, n1 squared h squared over 8m l1 squared plus n2 squared h squared over 8m l2 squared. I'm going to take out the common components, h squared 8m, and I can create the inside n1 squared over l1 squared plus n2 squared over l2 squared. Yeah, now we can do another step here, right? If you want, you can take another step, which is l1 equals to l2 and l. Now our 1D box is completely a square box, right? Then you can see there is another simplification can be done, right? A small simplification we can done. H squared over 8m, here n1 is the same, but the l1 and l2 term are now the same one, n1 plus n2 squared over l squared, which we can write as h squared over 8m l squared n1 squared plus n2 squared. This is our total energy term for 2D box. So in this next video we're going to talk about the normalization in 2D box.